Yes. So today we're very happy to have Leopoldo Pando Zayas today to talk about quantum black holes in holography. We are very happy you accepted our invitation. So when you're ready, please.
All right. So thank you very much. It's really a pleasure. I have to say that I've never been to Ireland. I have many friends and I love the literature. So I would like to get there sometime, but okay, for the meantime, this is what I can offer. I want to maybe apologize. I see a lot of experts and I thought the colloquium was more at the level of master students. So I will start very, very slow at the level of general colloquia. But then, of course, maybe I'll go more into technical details. But please feel free to let me know the pace to get with questions. Try to make it as lively as possible. All right. So yes, I want to talk about quantum black holes in holography. So I think these words are familiar to everybody here. I mean, there have been a lot of excitement in the news recently, right? The Event Horizon Telescope, the LIGO, all that. So this is very, very exciting. Just for a measure, when I was in graduate school, it wasn't completely clear that black holes were out there. So, but now, of course, there's no discussion. So I want to start, as I said, very low by just reminding you that black holes are solutions of Einstein theory of relativity, and they have these fascinating properties that were established back in the 70s by people like Hawking, Carter, Penrose, etc. And essentially, there are four laws, and that they are very analogous to the laws of thermodynamics. So there's a zeroth law, surface gravity is constant over the event horizon. First law, which is some sort of conservation of energy. Second law about the event horizon always increases. And just for a measure, I have written down the entropy of a solar mass black hole. So it's a huge entropy if you compare with matter. So, and this is really the question that we want to, so this is the beginning of the question. This immediately raises a number of puzzles and room for research, like what is the origin of this black hole entropy? Does the black hole entropy leads to losing information, violates quantum mechanics, etc. So of course, these are questions most sharply posed by Hawking in the 70s after his computation, but very quickly, well, not very quickly, after a few decades, he conceded, and this made it into the news. And I actually not just the news, but so if you look at this one, right, this is like a reprint of the news. So this was really in the big popular domain. This is a big thing. I mean, theoretical physicists don't often have this direct channel to the news, New York Times, etc. But this is important. And of course, if you should know that the reason that Hawking considered was essentially the ADS-CFT. So in the context of the ADS-CFT, you have a formula that is written here that states an equivalence of partition functions. So the quantum field theory partition function is equivalent to a gravity partition function where currents are controlled by asymptotic values of fields. So this is a very powerful formula, and that formula renders the information loss paradox conceptually vacuous, because if I can describe gravity using a quantum field theory, which is by construction unitary, then there cannot be loss of information on the gravity theory, right? So, and this is again the solution, the big solution to the problem. But of course, we are interested, and what I want to talk about today is, okay, yes, I agree with you, but how? Show me the money. So of course, I will not be able to show a resolution of the information loss paradox, but I can tell you, and my goal is to tell you a little bit about some very high precision counting of the entropy that we can do. So that gives you confidence that we are on the right track, we have the right theory, we are describing the right black hole. So that's as much as I would like to discuss in this. So the main target, of course, is the black hole entropy. This is a quantity that, as you can see, usually we set all these things to 1, but I just put it here again for the colloquium level part. So this is a formula, the entropy of a black hole, that contains a confluence of all interest in physics that we would like to understand better. Thermodynamics, you see Boltzmann constant there, relativity, the speed of light, quantum aspect, h bar, and of course gravity, right? G Newton. And what we would like to understand, first of all, is what is the microscopic origin of this formula, right? So we move from thermodynamics, right? Thermodynamics is a black box science, right? So it only says, my energy is conserved, so let's try to understand what's going on under this condition. But in statistical physics, we want to go a little bit into more detail. We want to see what is going on. So that is essentially our one big program in string theory. Of course, I hope you are aware of Strominger-Goffau, the first realization and explanation of the entropy in terms of microscopic degrees of freedom, very similar to our understanding of gas, of the gas in terms of molecules and molecules degrees of freedom. So this is the question that we have. What is the microscopic origin of black hole entropy? Now, there is a problem with the macroscopic entropy that I will explain. Well, not a problem, but so the first term that we always talk about is this one here, AOF4G. This is it's called the Bekenstein-Hawking entropy. Right? But in fact, as any observable, this is a quantity that receives corrections. And in this talk, I want to focus on these logarithmic corrections that the entropy receives. So they are determined by this coefficient beta, and they are proportional to the area divided by G for dimensionless needs, right? So the parameter beta is really a quantum parameter in the sense that it comes, and I will show you, from fields running in loops. So it's really a quantum property of the theory in which a black hole lives. And so the goal that I have, and what I would like to describe, is some of the progress that we have achieved in computing beta, this number here, the coefficient of the logarithmic correction, using both the gravity side and the field theory side. All right. So that's sort of the goal. The main character of the whole colloquium is this beta, right? So we will compute beta in many examples, and we will try to see what do we learn about the theory by computing beta, and whether, of course, we have agreement between the field theory side and the gravity side of the ADS-CFT correspondence. That's the main part. All right, so I will not. So this was again, at the colloquium level, this is to motivate undergrad students and maybe master students. But I think here it's a little bit vacuous, but I want to mention that essentially, like in any counting problem that we know from undergraduate physics, at the level of Kitter and Kromer, our answer would essentially end up being some ratio of factorials, right? So this we know from the harmonic oscillator, and this will be true for n equal 4 supersymmetric Young-Mills. So it's just going to be some ratio of factorials, but very complicated or very fancy, right? So elliptic gamma function, double sign function, it will be something, but the root, right? The underlying principle is just this. So if you are not string theorists and you don't care about a lot of the details of what's happening in our community, you can paint all this activity with a broad brush, saying, oh yeah, they are computing generating function for some field theory, and of course they have to be fancy versions of the harmonic oscillator. Right? That's what happens. So here's the first field theory object that I want to discuss. So black hole microstate counting. So we want to now use the ADS-CFT. So instead of okay, so what is the object in quantum field theory that we want to compute? We want to compute this object here, the topologically twisted index. So if you look at this part, it looks like a regular partition function. Now, because I have charges, I will weight my charges with some chemical potentials delta. So that's it. And then, of course, I'm in the realm of supersymmetric theories. So I'm going to use this -1 to the f to have more control over my physics. And this is just a Witten index, basically decorated Witten index. Now, a theory that we are particularly interested in understanding is this Abjm theory. It's essentially a Chern-Simons matter theory. The gauge group is UN cross UN, and it has levels, a Chern-Simons level K and -K. And this is the quiver, so you can see there's matter in the bifundamental representations. and then it has SO8 R symmetry. So that breaks down to the Cartan of U1 to the fourth. So the charges that I was mentioning here are going to come from the Cartan of SO8. And that's essentially all that is required. So once you have this theory, you can compute, you can go ahead and try to compute the partition function. Now, this partition function is computed with a magic trick, which is called localization. And that's it. So you have the theory in the appropriate background, you perform localization, and this is the answer. I don't want to go into a lot of details. I will try to describe what's needed. The important thing here is that you can write this partition function as the sum over Bethe-Ansatz equation. So here I would like to mention the work of Nekrasov and Shatashvili. This is work that permeates a lot of what we do. And again, that's just the solution. You find this, that's how you construct this topologically twisted index. You find solutions to the Bethe-Ansatz equation here, the Bethe-Ansatz equation. You find the solutions, you plug them back, and you have your index. And so just because Anna was mentioning, this is something that we have learned to do in a very clumsy way. So we can get the leading term, we can get subleading terms using a lot of brute force, but there's really no good understanding of this problem. And I think this problem can lead to exact quantum entropy of black holes. So it's quite interesting. And I think maybe some synergy with integrability can really be useful to get insight into this problem. All right, so let me summarize what I was saying about the topologically twisted index. So yes, I have an observable. This observable will count eventually the entropy of the dual black holes. But I have an algorithmic way of computing it. So given some chemical potentials or Fugazi psi delta, and these holonomies xi and si tilde, I have a system, essentially a system of 2n by 2n equations. So once I solve the system, I plug it back into the expression for the partition function, I have my answer. And it is quite crucial that this answer is exact in n. So of course, I can go to large n, and the large n is great because it connects nicely with gravity, but I can just compute it at finite n, and that would be an exact answer. And that is good. That is great because then it allows me to just numerically, and this is what I was saying by brute force. So I don't know how to solve this, the thermodynamic limit systematically, but I can deal with matrix models. So I have a matrix model, I solve it, and I can. So this is something we did. In fact, there were some undergrad students at the time helping with this because it's just a very well-defined algorithmic problem. So find these equations, plug them in Z, and give me a fit, an expansion. And what you see from this table is that this coefficient here, this -1/2, is fairly robust. So we can change the fugacities, we can change the magnetic charges of the solution, and the answer is robustly -1/2. So now I have solved my problem in the field theory side. I know what is the coefficient of the logarithmic term in the field theory side, and I want to tackle this question on the holographic side. All right, so that's what I want to do next. But before that, I want to also emphasize that we, with another student, we perform similar calculations at the same level for many other different theories. Here are some quivers as example, not just the Abjm, which is, let's say, some of the simplest, but much more complicated quivers. We perform the same computation, and we get precisely on the field theory side this answer. So now when I go to gravity, I would like to not only explain the -1/2 log of n for ADS4 × S7, the dual of Abjm, but for a possibly large class of ADS-CFT pairs. So that's my goal now. So maybe I can stop here just to make sure that the audience is still with me. Are there any questions? Is the pace okay? Okay. So, all right. So here's the ADS-CFT pair that I've been discussing so far. So it's the 3D Chern-Simons matter theory is dual to a string theory or M theory on ADS4 × S7. And more specifically, the topologically twisted index is going to be equated to supersymmetric magnetically charged black holes in ADS4 cross S7. So here I have written the black hole. I just want to highlight a few things for people who don't see black holes on every day. So essentially the black hole that you know, this is to be compared with the Reiner-Nostrom black hole, which is a charged black hole. And usually this function here is 1 minus 2m over r, and then you have plus q squared over r, right? So this is roughly what we have now. Instead of 1, I'm in ADS, so this is clarifying for me that I'm in asymptotically ADS4. And then, you know, because I don't have, well, m and q must be equal for supersymmetry, I end up with this expression. So this is your regular Reiner-Nostrom black hole that you know from the grounded GR, just in asymptotically ADS space and supersymmetrized. So in a way that the mass and the charge agree. The charges, of course, come from this magnetic field here that I have written. So that, and again, it goes through the Cartan of SOA, sorry. So that's the solution. The solution, you can upload it or uplift it to ADS4 cross S7 in M theory. That's the solution that we want to understand. Notice that the entropy is quite complicated, right? So the entropy, I drew it down here. And you can see, right? So it's given by the charges, and I are the magnetic charges. It's given by the charges, but it's quite a complicated function. So F2 is this combination of product of charges, and then theta is this other expression. You plug all that in, and that's the charge. So the fact that we can reproduce the entropy of such a black hole using a field theory computation is not trivial, right? It was not an easy question of scaling. In ADS-CFT, oftentimes what happens is that conformal symmetry fixes everything. And you essentially are saying, and your argument at the end of the day is an argument about conformality, which is not the case here. Here, to get this expression, you really need to understand what's going on with the charges. So let's see. All right, so what I show you the background, right? So I promise a gravity computation of the log. So I show you the background. What I want to do now is to consider fluctuations around this background in 11-dimensional supergravity. And that, you know, that one loop effective action will be will give the correction to the 3-level action, right? Which gives me the entropy. Right? Now, why is this important and protected? The most important thing is if you tell people I'm doing quantum gravity in 11 dimension, that's already you know, people can dismiss you immediately. So I want to argue first that I'm computing something that makes sense. I computed in low energy quantum field theory, and that makes sense. And so here's what I want to explain. So this kind of computation sometimes we're sort of name an infrared window into UV physics by Ashok Sen. And the reason is this, right? So the logarithmic correction that we are interested, they can be determined macroscopically just from the gravity theory. And all you need to know is the massless spectrum of fields. That is insensitive to the UV completion. One, they usually are, therefore, a very important consistency check for enumeration. So in the context of the Strominger-Buffer, you had a string theory answer for the logarithmic correction, and now you can use gravity, which is something Ashok Sen did a few times, to check that the logarithmic coefficient agrees. And this is, again, this is because it's sort of independent and you can compute it just with the IR data, it's a very powerful tool. So now let's go into details very briefly. So the one loop effective action around sub-background is essentially computation of determinants. There's no interaction. So all I'm doing is some Gaussian integrals, right? And now these functional determinants are going to be, I'm going to define as the product of non-vanishing eigenvalues. There are many, many of them. And there's technology that allows to do that very efficiently. These are these fictional techniques. So what I have said is that I'm going to compute the determinants of some of the modes that enter in this background, and I'm going to be using Hill-Kernel techniques to extract them. Now, there's some important facts. So first of all, and this is why, even though this is a gravity computation, I want to emphasize robustness, because this is the coefficient of the log. So there will be logarithmic divergences, and the UV scale enters there. So you can change the scale of UV, but the coefficient will not change. So that's the sense in which I'm saying that this is very robust. I can show you some details if you want how to implement this in the heat kernel, but this is very important. Now, on top of that, we have that in odd dimension. So this computation is very similar to the computation of conformal anomaly. Right? So if you remember that computation in odd dimension, there's no combination of the Riemann tensor and the Weyl tensor that you can construct that will have the right dimension, and therefore there's no anomaly in odd dimensions. So similarly here. So in odd dimensions, the only contributions that you can get to the one loop effective action, they come up from zero modes, or sometimes people call them boundary modes. But essentially, because we are in 11-dimensional supergravity, all we need to worry about is understanding what are the zero modes, how many zero modes contribute. This and 0D here is the number of zero modes. This, it goes over all operators, right? Bosonic or fermionic. And then, because I'm using the heat kernel, I have to subtract one. The heat kernel includes the zero modes there, and then I add them with the right scaling. But this is all a very well-known prescription, and it's been applied by Ashok-Sen to string theory black holes in various papers. So now what we want to do is do this for 11-dimensional supergravity. I remind you that the content of 11-dimensional supergravity is a graviton, a gravitino. There's a three-form field, right? And then ghosts. But the ghosts, there's a very beautiful paper in the 80s by Ziegel. It's called ghosts of ghosts. So to quantize a ghost, you have to fix the gauge, but then you use a ghost to do it, and you have to do it for that ghost. So there's basically a tower of ghosts. And so to quantize the three-form, I need two-form, one-form, and zero-form ghosts, and they of course alternate the statistics. Now the one loop contribution comes, there's only one two-form zero mode in ADS4. S7 doesn't have any zero modes. So there's only one zero mode in ADS4, and that contributes to this two-form zero mode that enters in my quantization. And the number of zero modes, how many? I compute using just the Euler characteristic of these black holes. And there's a detail here, technical, that you need to approach the stream of black holes through the non-streamer branch. But if you do that, then this is your Euler characteristic that you get. So now you plug everything into the formula that I told you for the one loop correction of the entropy. And essentially you get this -3 log of L, but the length in ADS, part of the ADS CFT dictionary, tells you that this is 10 to the 1/6. So you reproduce from the gravity side precisely the -1/2 log of N. So this is something I published with my former student Vimal. Wen Li here is now a graduating PhD student from Princeton, so he was undergrad here, and then my colleague Jim Liu. So I promise, so this is the computation for black holes in ADS4 cross S7. I promise that there's in fact a whole family for which we can do the same. So this is S7 is what I just discussed, but there are many 7-dimensional manifolds, Q111, V52, and 010. I hope that you know some of these numbers, but essentially I'm talking about any Sasaki-Einstein manifold, 7-dimensional manifold. They would have made supersymmetry. They would have these black holes as solutions. And for those, I can do the same counting on the supergravity side. And the only requirement, right, is that I had a two-form zero mode. So if there are no zero modes in the M7, and in particular for every M7, and for every M7, which is a 7-dimensional compact Einstein manifold with positive curvature, there's no one-form zero mode. The first Betti number is 0, so my computation is exactly the same. And I just now realized that this is true for the whole class of ADS4 CFT3 pairs. So that's sort of one interesting result of comparing the beta. Remember, my goal was computing this beta in the field theory and on the gravity side, and I have done that. And for this large family, I have complete agreement. All right, so there are extensions to this computation. So in flat space, of course, you remember the horizon topology theorems of Hawking. So the horizon must be a spherical symmetry. There's way to prove that. That is not true in gauge supergravity. Asymptotically ADS, the horizon can have different topology too. In particular, it can be an arbitrary Riemann surface. And you can run the same script and you on both sides, and you get precisely this correction. So the example that I present here, ADS4, using the topologically twisted index, I use some numerical analysis. So some of my string theory colleagues are a little bit suspicious of numerical analysis. But we also reproduce similar results in a completely analytic setup where we use other techniques. I'll discuss that momentarily. And then, of course, we can generalize these computations to, I have discussed only magnetically charged black holes, so I can do a similar computation for rotating an electrically charged black hole. So that, I think, covers a big class. And that's something that I've been doing in the last 2-3 years. I'm very happy about that. So I would briefly want to mention the analytic setup in which we can perform similar computations. So there are different ways to get these ADS4 CFT3 pairs. So the ones that I have been discussing they come from M2 branes. So you look at the transfer space of N2 branes, and then you discover that it is a cone over this 7-dimensional Sasaki-Einstein manifold. But there's another way to construct them in the ADS-CFT correspondence, in which you have an M5 brane, and you wrap that M5 brane on a hyperbolic 3-manifold. And here's a table. There are many entries, but the important thing is that, first of all, we know the entropy, and we know this scaling. And oops, I think I have a problem here. I have to restart Microsoft. It's sort of crashed. I don't know exactly why. Just 1 second. All right, so it did not. Okay, sorry about that.
It's fine now.
Can you see the screen now? Everything is okay?
Yeah, it's everything.
All right, awesome. So I was saying that there are 2 different ways to obtain ADS4 BACFA. There are many ways, but there are 2 central ways in ADS-CFT, and one includes, oops, oh, sorry. Laser pointer. And one includes taking an M5 brane and wrapping on hyperbolic 3-manifold. And we know the dictionary fairly well. Okay, so for this situation, one can use the 3D correspondence. Is a correspondence between certain 3D conformal field theories and Chern-Simon on this hyperbolic 3-manifold. So you can read the observables of the field theory if you know the Chern-Simon information. This is something that has been developed in the mathematical literature, and also mathematical physicists, Sergei Gukov, Dimofte, Gayot, etc., had contributed considerably, but I am just a user of information. So for this partition function, I can construct the topologically twisted index or the superconformal index using some building blocks. Some of them are the 100-gluing operator and the fibering operator, and I can read them from information in Chern-Simon. So they are either the Atiyah-Singer torsion, or they are just the classical Chern-Simon action evaluated there. So I will not go through a lot of details, but one improvement that we made in collaboration with Dong Ming, Francesco Benini, and Kim was essentially that now the 3-manifold, the hyperbolic 3-manifold, can have really non-trivial first Betti number. And in that case, there would be contributions that come. ADS4 still had the 2-form 0 mode, and I can wedge that with a one-form zero mode of the hyperbolic three manifold, and that will also contribute to the entropy. And what we found is, of course, this is the contribution. So you just, the number of zero modes comes now, I will have as many as, obviously, the Euler number times the first Betti class for the hyperbolic three manifold. And this contribution is precisely what we can obtain using the field theory and through the 3D correspondence. So this is a slightly more general for hyperbolic three manifolds with non-trivial first Betti number. And again, the agreement remains. All right, so this was a lot about ADS4 cross CFT3. So a natural question is of course, why didn't you start from the canonical example, right? ADS CFT, we always think about ADS5 cross S5, what's going on. So what is going on there is roughly summarized in this slide. So of course, I have four-dimensional n equal 4 supersymmetric Young Mills in 4D, which is dual to type 2B string theory. This is the most studied example, but this problem was attempted. This counting of entropy was attempted in 2005 by Kini, Maldacena, Mingual, and Raju. And at the time, it looked like it did not agree with black hole entropy, because the answer in 2005 was order n to the zeroth. And we know that the entropy of black holes should go as n squared because it's related to the Newton's constant. But at the end of 2018, three groups independently came up with a way to fix that situation by essentially consider complex fugacities that allows you to explore different regimes. This is now much better understood in the context of analytic structure, and you have to go to the second sheet of the index, and there you find your n squared degrees of freedom. And that would, of course, was matched to the area divided by 4G. So you already suspect that my first question was, okay, what about log corrections in that context? That's sort of, I want to see, well, let me explain, since I have time, let me explain my motivation, right? My motivation is not just that I can I compute because I can. So there's one example that one historical example, which is the hydrogen atom, right? So Bohr, when I was in high school, a teacher of mine explained the hydrogen levels, and his explanation was really like, well, you have this planet, and then you have the sun, and the angular momentum of the planet is quantized. And as a high schooler, you can get a formula that looks like Bohr formula. Of course, you have no understanding of the physics. You don't know, the wave function of the electron. You don't know any of that, but you still have the right number. Now, the entropy of black holes is slightly such a Bohr formula. It's very universal. Whatever you do, you'll get it, right? So it's always area divided by 4. It could be that I wrote area divided by 4 by some stupid mistake and still got the right answer. So I think it's important when you have such a universality to probe a little bit behind. See, okay, my counting is really agreeing, at least agreeing. And we'll go back, towards the end of the talk to talk about other approaches. But I think, it's not enough. It's really not enough to say, well, I got the leading piece. I understand this, because there are many situations where that simply is not true. So I wanted to study the superconformal index of four-dimensional field theories, and I did it with, again, my former student is now a postdoc in Korea, Alfredo, and former student here, Jung Ho, and my colleague Jim Liu. So we study the superconformal index of n equal 4 theory. So by now you know what I'm trying to write. So -1 to the f because it's an index. This part, of course, will be independent because I'm counting only states that are annihilated by the supercharge. Q is these are electric charges, and J1 and J2 are basically angular momenta that you can have. So as I promised at the beginning, the answer is this elliptic gamma functions, but again, gamma function is a generalization of factorial, and elliptic gamma function is a generalization of gamma function. So you see that, lo and behold, we are just really looking at some factorials in a fancy way. But we have the answer. What we managed to do was to expand this and to really understand what's behind this integral and write it in a way that it demonstrated, well, first of all, we have an expression in which for large angular velocities, for large angular momenta, this expression is exact in n again. And the answer is quite interesting. You see here I wrote in terms of, this is some constant A calligraphic, but Z is the partition function of a field theory SUN on S3. And this again,
Quick question. Sorry.
Please.
There will be lots of instanton corrections here. So you are taking larger limit and it kills the instanton corrections?
So this is the theory is on S1 cross S3. So this is not on S4 on another place.
No, but still there will be monopoles. Call it what you want. I mean, there is there are the solutions like instantons, monopoles, and there is an infinite sum. So this answer is a one loop answer because it's exact. But then there is a instanton, or there is a reason why they are killed.
I think for the superconformal index, they do not contribute. And again, the way that I can see it is once you do the localization computation, you look at the locus and the locus does not admit, there's no instanton in the locus. So for example, in the Abjm S1 cross S2, there were magnetic monopoles that contributed, and one has to be very careful in including them. That can be done precisely using Bethe ansatz. So here I think that the localization locus simply does not have instanton.
Sorry, one more. So if I would do S1 times S1 times S2, okay?
Yes.
I would have lots of instanton corrections. So I mean, this calculation I did with Nekrasov, and it's actually very interesting. It's a 4-dimensional theory on torus, which somehow relates to Bethe ansatz of XYZ model. So now somehow, I mean, I probably missed this point, but once I replace S2 times S1 by S3, how do I get, probably what happens that this is the answer in large N, and then if you can calculate 1 over n corrections, I will start getting the correct contributions from, not instanton in this case, is monopoles, but something like that. Because I know for sure I calculated S1 times S1, so torus times S2, or actually torus times any sigma. Okay, take sigma 2 manifold times the torus.
Yeah, so there I do not, I mean, there I absolutely agree with you. In that case, there would be corrections. The only good thing about those in 3 dimensions, S1 cross sigma G, as you said, is that you are able to sum. So they are part of the localization locus. You have to sum over all of them, and that sum can be done using some Jeffrey Kirwan.
It's a dilogarithm. So that sum is definition of dilogarithm, basically. So you get dilogarithm when you sum it. Again, it's when it's S2 times S1. But what I'm saying is, I know answer also S2 times torus. So S2 times S1 times S1. And that answer, again, is connected to Bethe ansatz of XYZ model. Exactly like S2 times S1 or sigma times S1 connect to Bethe ansatz of XXZ model. When you go one higher dimension 4, it is XYZ. Now, what is tricky here, and this is what I'm interested now to understand, is that instead of S2 times S1, when I put S3, I lose something, you are saying. Somehow contributions of those instantons disappear. And this is, I mean, I should know probably, I'm very sorry, I'm asking you, but somehow I don't understand whether, maybe it's large N, that's a trick. Because in large N,
I don't think it's large N. I think it's really the locus. There are no, right, because you have S1 and essentially the holonomy on S1 remains as part of your locus, and you have to integrate. But then on S3, there is no configuration of the gauge field that will contribute to the BPS equation, right?
No, sorry. I take 4 manifold, S1 times S3. And let's calculate contribution of theta term, right? Integral FF dual.
Okay.
That's not 0. There is a configuration. I mean, it is whatever, second Pontryagin class.
No, it has to be self-dual. And how can you do self-duality in S1 cross S3? Because you need legs.
That's Werner Nahm. Werner Nahm solves the equation what is self-dual equation in S1 times R3. He did R3, but still, I mean, S1 times R3 is called the NAM equation.
Okay.
Right? And it's certainly not empty. Where is Werner? Is Werner here? Denjo, is Werner around?
No, he's in Germany at the moment.
Oh, okay. So Werner Nam wrote this NAM equation, which is S1 times R3.
I see.
And it's a very interesting contribution. I think what happens, it's exactly like, I remember Kostya Zaremba's work on large N when he claimed, I didn't follow probably, he said that in large N, only what matters is the gamma functions, the one loop contribution. The rest of this stuff goes away. And then it's a Barnes gamma, product of gamma functions like you had. Probably trick is large N. This is my conjecture. I'm sorry I interrupted your lecture.
I see. No. I'm very, obviously this is great insight that you're sharing.
What I was wondering if this XYZ model shows up, because
this is exactly one of the questions I was mentioning at the beginning. So there.
Sorry, I missed. I was on the meeting.
No. It's just that. So there's a lot of knowledge that the integrability people have, and people like yourself who know the answers very well. And as I openly say, so I'm a user of many of these results, but I can see that a deeper understanding can lead you to a better understanding at subleading orders. And
right. So the Zaremba said that all the difficulties of instanton corrections disappear in large N, and what you end up is now next step will be the beta ansatz that comes up, only first term which comes from the gamma functions. And interestingly, what comes from gamma functions had the consequences. What Kostya had, I think, was a large N limit of S4, instead of S1 times S3, if I remember correctly.
Yes. And, he has a S4 partition.
Right, S4. But what I say, sorry to kind of the Pontryagin numbers, so theta terms contribute on finite size for manifolds. Donald said there is some numbers there. And as I said, in case of S1 times R3, this reduces to NAM equation, which have profound consequences usually. Right? So I actually was dreaming to find the relation between NAM equation and beta ansatz, but I did find one, which is a Hitchin equation, which is when you take S1 times S1 times Riemann surface. Then it's a Hitchin equation, okay? That's what Nigel did. And that one was a relation between quantization of Hitchin and through beta ansatz and the supersymmetric surface. But this one had to have profound element from NAM equation. But what is probably true, and that's what Zaremba was saying, that Samson, in large N, you don't see any of it. So only gamma functions. This is because your formula is a one loop formula.
I see.
It's just determinants, right?
Yes. Yeah.
Sorry.
No. Thank you very much. Yeah, I have to admit, I know Zaremba's work, and I see the localization locus there. There are solutions that are like instanton, but okay, there's another. Perhaps I need to look at this more carefully, but you can also, because these are essentially, you're computing the superconformal index, you can also compute it in the Hamiltonian approach where you just counting operators and you just count the...
Yes. Since we have this conversation, I can tell you this, listen, there is this standard statement that for n equal 4 super Young-Mills integrability, there is no what's called the Young's function, okay? So basically there is basically every integrable system has this Young's function, except integrable systems that were discovered for n equal 4 does not have Young's function. But one of the ways to discover Young's function is to do this calculation. Because what is standing in the integrand logarithm of that will be some function, critical points of which will be beta equations. Now, for XYZ, there is a Young's function. It was written by Takhtajan and Fadey in 1979, and then by Skliani. So what I was claiming 10 some years ago is that actually properly done, this type of calculation should lead to Young's function for n equal 4 integrability, which everybody like Kazakov and Zaremba, all of that, there is no Young's function for n equal 4. The hunting for Young function is important thing. And conjecture was, which I made probably in 2011, was that you can write Young's functions through solutions of NUM equation, the exactly same way that I and Nekrasov did for the Hitchin equation.
I see.
So somewhere in this calculation, but as again, Zaremba was saying, it was like 2-3 years ago here, that in large n they disappeared. So only one loop remains. That's probably, if you would want to calculate finite n, that would be very interesting.
I see. I see. I see.
Okay, that's all I have to say. And
thank you. Thank you very much. So just to reiterate, in fact, we can try to compute this logarithmic correction, which is sort of my goal. But I want to emphasize again, there's an approach to this index that uses the Bethe-Ansatz approach. Unfortunately, not all solutions are known. And basically, the space of solution seems to be a nasty space in the sense that there might be a continuous parameter of solution. So it's not countably nice. But if you take just one solution, which is called the basic Bethe-Ansatz solution, and that seems to be nice in the sense that in that case you have a torus parameter that helps you. You can evaluate, but the key point here is that we evaluated the superconformal index using the saddle point approach and using this Bethe-Ansatz approach. In both cases, we get the same. This is large n. All I need is the large n result. Give me a contribution which is proportional to this large n. So at this point, I wanted to, okay, this is the grand canonical. What I explained was the grand canonical answer. So I want to go to microcanonical, which is what I compare directly with black hole entropy. I get this number, -2 log of n. So that's it. That's the logarithmic correction to the entropy of ADS5 black holes as computed from field theory. And it would be nice to now show you the computation, the supergravity computation of one loop determinants and that it agree. But unfortunately, that actually is an open question. I have tried. There are a lot of more technicalities, and I can explain very briefly what's the problem. In 11 dimension, I had no conformal anomaly, so I had to focus on 0 modes. Now I'm in 10 dimensions. 10 dimension is even dimension, so the counting is a lot more complicated, and I have made some progress, but that's not completely there yet. But I will switch gears and try to tackle the problem using a slightly different point of view. And this point of view relies on something like a more universal description of what's happening with this gravitational solution. So of course, the ADS-CFT community, spin theory, we are very happy. We are elated that we have now this result and we can go to one loop and check. But of course, I mean, we know the principle of renormalization group. We don't expect that to really understand any black hole, you will need to go all the way to string theory. And there might be intermediate ways, sort of symmetry-based method that allow you to compute some information. The question is how much information, but that do not require really using the full string theory. And that's one approach that we will have for this ADS5 black holes. So what I have been discussing in the talk so far is this top line here, using ADS-CFT to connect directly ADS black holes to the field theory dual. But I can use this technique. It's essentially go to the near horizon, focus on the near horizon geometry. That geometry is locally an ADS3 geometry and has a Virasoro central charge of asymptotic symmetries. So that goes under the name of the Kerr-CFT. This was introduced in 2008 by Strominger and collaborators. And more recently with my postdoc, Jun Mian, and also my student, Marina David, we were able to adjust this computation for all black holes in ADS-CFT for, dimension 4, 5, 6, and 7. So this is now also, at least it gives you a unified approach to the entropy of black holes. So you have, again, we have achieved this as a community, but I now have a lower energy, not as powerful, but very universal approach to the entropy. Now, once I'm in this line here, down here, what is my data? My data is, I have a CFT with some global charges, which are here characterized by P1. So it's some generalized, some Kac-Moody Virasoro algebra. This partition function has modular properties that we know. And from that, that's enough for me to read the density of states. Now, the density of states, I can do at tree level, as a saddle point. This is the famous Cardy formula. And I get an expression. This expression coincides with the Bekenstein-Hawking entropy of rotating ADS5 black holes. But I can also do a saddle point approximation in this Laplace transform of the two-dimensional partition function and get a correction. And the correction that I get agrees precisely with the field theory correction. That is why, again, it's not directly a type 2B computation. It's a computation that relies on near horizon symmetry-based analysis, but it agrees with the answer from field theory. So that's all I have to say about ADS4 and ADS5 black holes. In the last few minutes, I want to sort of stay in this land, step back, and try to understand what of all these concrete computations that we have done within the ADS-CFT, what can we extract that we expect is true for any quantum theory of gravity, right? That's a bigger question that would be nice to also address. So in general, in any theory of quantum gravity, there will be two kinds of corrections. One kind is this quantum corrections of virtual particles propagating in loops. This is what I have been discussing today. There's another possibility, of course, in the EFT approach to gravity, in which you have Einstein-Hilbert as the lower dimensional operator, and then you can have higher derivative operators. And it would be nice to understand also if we can reproduce that correctly. So in this paper from 2009, well, sorry, from 2020, with Joel, we explore ADS4 black holes. So all higher corrections that can come to this ADS4 black hole, we can use the Sen entropy function to compute them and to understand them, and that was successful. So that tells me that I understand all higher curvature corrections from this lower dimensional point of view, and they seem to agree with what we see. And we have ongoing work approaching the same problem for asymptotically ADS5 black holes. So again, we go to the near horizon of this ADS5 black hole, we have Sen's entropy function principle, and we check whether all higher curvature terms can be accounted for that way. And so far, it looks like this is positive. So here's the picture, slightly more ambitious. So I have discussed quantum corrections at this level down here, where I take some near horizon geometry that allows me to have this Virasoro central charges and compute the degeneracies. But there's another direction. This is more related to JT gravity and such the Yuki-type model, etc. So this one is less. Or again, I'm having some issue with this. Let's see if this happens. Can you see my screen?
Yes, but it's kind of stuck, and yeah. So
yeah. So let me do it one more time. But again, what I'm saying is that we have had certain success understanding black holes in ADS-CFT, and that's great, of course. But it would be nice. It would be nice to see how much we really can get out of this just by more generic principles that are based on what is the symmetry near the horizon, using that data. And again, there's this area of connecting using JT gravity and SYK that would be an interesting direction to pursue. So I want to finish with some of the lessons that we have extracted. So after this precision counting, I have shown you agreement beyond the leading piece. I think this should be convincing enough to say, okay, maybe now is the time to try to set up some dynamical question. There's one key dynamical question in this business, which is Hawking radiation. So can the field theory now tell us not just how to count precisely, but more importantly, whether we can access Hawking radiation using that? That's one of the directions that I find very appealing. So the information, as I said, is conceptually back using the context of ADS-CFT, but now I think we have the tools to try to answer how. And so the process of Hawking radiation, it seems to be hard to tackle directly from higher dimensional theory, but perhaps using the lower dimensional approach, we might have some success. In fact, there is a number of toy models right? That reproduce the page curve for some ADS-like black holes. And maybe it would be nice to try to connect this with more realistic black holes. So, and again, one important thing is, how much of this is really heritage. It comes from string theory, but it's true for any theory, any general theory of quantum gravity. So I wanted to finish my talk with this workshop that we have been organizing at Stony Brook already since 2019. That was before the pandemic. So the pandemic has made us push and push, but now it looks like it's going to happen in November of 2022. So if you are interested, register, and this would be a really nice place to continue talking and learning about this. So especially for the integrability people, I think that would be a great service to the gravity community to straighten out how to compute carefully this solution. So thank you very much.
Let's thank Leopoldo for the very nice talk. And then, if there are any questions, please unmute yourself.
I do have 2 questions, but I want others to ask. I'm sorry.
I have perhaps a more physics-oriented question. The ADS black holes that you're talking about are large ADS black holes which have positive specific heat, whereas physical black holes are closer to the small black holes in ADS, which have negative specific heat. Can you comment on how you would hope to access the negative specific heat ones?
Yes, good. Very, very good question. So, yes. So at the moment, there's some approaches to small black holes. So we might be wrong. The idea is that once you compute the index, the index has been explored in this regime where n is large and the charges are large, and that corresponds to large black holes. So there should be people have tried to numerically compute the index, and it's very hard to get to the intermediate regime that you would need to see small black holes. But in principle, they could be there. That's sort of the main, that's the situation right now. Now I want to take the chance to highlight something that people are very excited, which is the fact that we now have some understanding also of rotating black holes. So in a sense, rotating black holes are closer to astrophysical black hole in the sense that we hope that what we learn about them is really might have more applicability than just the typical, magnetically charged large black hole, etc. Maybe rotation is the right thing to point to.
I have one question and one comment.
Please.
Can I? Let me start with comment, actually. Your last slide was saying that you would like to have Hawking evaporation kind of explained with standard field theory methods. Yes. And I kind of doubt that, because if it's a correct calculation, as you mentioned, Lisa, there will be no violation of unitarity, which means that you will not see, it's in a setup of S matrix, when you're calculating some kind of process, physical process, in a proper quantum field theory, you will not get non-unitary answer. Now, what Hawking did, he assumed that there is a large black hole and there is no back reaction, and so his calculation and evaporation and so on was intermediate in a sense. So proper answer will give you unitary answer. You will not get evaporation like what Hawking got, because it has to be unitary quantum physical unitary quantum field theory.
Good. So let me address that. So that's very nicely connected to the previous question, right? So these are positive specific heat black holes, and as we know, right, in ADS, the radiation is not going to escape. It goes to infinity, bounces back. So what I meant here is it must be modified. So it must be more along the lines of what people are trying to do now, which is coupling or decide. You have to decide what to do at the boundary, maybe couple to something else, and allow your radiation to leak. And if we can compute that rate, the radiation is leaking for your system, and compare that with black hole Hawking radiation, that I think would be the right, but you're right. So just
most likely in a conventional quantum field theory language, kind of approach with d-branes, not decoupling, is a more proper one, because think this way. So what is the problem with Hawking radiation is that in time goes to minus infinity, there is a one space asymptotic limit, which is infinite. But when the black hole is formed and there is a horizon, you have to expand in two asymptotics. One is horizon and another is infinity. So Hilbert space in the past and Hilbert space in the future are not isomorphic. So this is not a standard setup of quantum field theory when we teach students that we have to consider physical processes when Hilbert space in and out are isomorphic. Otherwise, there is no definition of scattering. Now, what Hawking had, in that sense, more like looks like that you see you have a d-brane somewhere there, sticking in, like in a Kondo problem, and it does not decouple from the bulk, and there is a leaking of information there. But if you consider complete theory, it's unitary perfect. But if you now take approximation, when you think that whatever happens in a d-brane is, you don't observe it somewhere, whatever's there, basically in a Kondo problem, it would correspond, you don't quantize the defect, right? You would get non-unitary answer. So I actually doubt, I think Hawking, when he admitted some losing of some bet, did say something like this. And Zeldovich used to say that this calculation, the biggest problem is what I just said, that the past and future infinities in time don't have isomorphic Hilbert spaces because there is a horizon, you have to expand with respect to horizon. Now, my other question, actually, this is philosophy, sorry for this comment, but the serious question, what do you expect in this analogy? You had this slide of JT gravity and SYK and so on. What calculation I have to do similar to these calculations that include beta ansatz and so on to get a relation between JT gravity expansion and SYK answer, as Saad, Stanford, and Schenker claimed, that it's not one theory, but it's a sum over theories. So what I have to calculate things that I know, I mean, in things that you've been describing, to see that on left-hand side, I have this sum, right? Like in JT gravity, Saad, Schenker, and Stanford had. And on the right-hand side, I have something in SYK. So this will be some kind of calculation that you showed us, and expansion would be 1 over n. So their expansion will be like 1 over n expansion. Basically, what is relation of your type of things with SYK and JT gravity? Can you more elaborate?
Yeah, so let's see if I can share the screen, because this is essentially something I'm working. I was mentioned because come on. Just 1 second. It takes me a few steps to get to.
That's okay.
So what I described here, and the way that I was able to get the subleading correction to the entropy of ADS5 was I took some limit, geometric limit, right? And then the geometry takes this form of curse CFT type. And here I did the counting, and I performed the counting even all the way to logarithmic term. So now I could take a limit, geometric, a near horizon limit, in which in fact, you can see that ADS3 is like a foliation of ADS2. So ADS2 is there. And the limit here is a limit, like you go to the near horizon, you go to low energies, and you can see that the effective dynamical degrees of freedom there are fields in ADS2. So they are generalization of JT gravity, but this I can already see in my solution. So maybe because I think I had a formula. Let me see if okay, I don't have a formula, but anyway, if you take any of this ADS black hole, let's take ADS5 black hole, you can take a limit to the near horizon, and it will look like a ADS2 geometry with many fields floating around. That is a generalization of JT gravity. Now, I don't know what to do on the gravity side. On the gravity side, I was for a long time thinking that there is some reduction of the field, on the field theory side, there is some reduction. If you think of the field theory as saying I want to focus on a specific set of operators with some charges. It could be that the effective theory of those operators is really an SYK-like theory. Now, the more complicated questions of replica, etc., I don't know how they appear, but the
No, sorry, my question was, I think, easier. You know, left-hand side on this slide, which is ADS2 geometry and so on.
Yes, yes.
It's actually two-dimensional quantum field theory, which is not JT gravity. It is more like coadjoint orbit action on Virasoro group. It's actually a piece of two-dimensional gravities that Polyakov had. And that thing does have a limit in which it gives answer of SYK. That statement is correct. Because basically on the left-hand side, you are talking about some Virasoro algebra and so on, some characters, and SYK partition function is a limit of the Virasoro character. So that line is clear. What is not clear to me, how to get this as when you go down from ADS5, how to get
no,
this.
that's actually not a problem. I can show you. I thought I had the formula here, but it's just very, it's very, I don't have a formula, I'm afraid. But no, this is mechanical. So there's some limit. You need to take the radius and you need to go into some co-rotating frame, and you land in a geometry that is really... That
one, left-hand side, I understand. I was asking about right-hand side.
Right-hand side. No, there I don't know. What the best thing that I did not make it work. I could not make it work. I was trying to... So what I was trying was similar to the BMN limit, right? You start in BMN, if you remember, you start in n = 4. You take large R charge and large conformal dimension with the difference being constant, and you land in a set of operators, right? You land in a theory that looks, well, is the PP wave, but it's a sector of n = 4 that is integrable and that you can try to understand. These black holes, they have a very clean scaling of charges. This includes now angular momentum. And I don't know exactly, but I was hoping that tracking the operation.
So you want to get it from counting problem, but I would rather say right-hand side is a conformal field theory, right? So take the 4-dimensional conformal field theory on the right-hand side. What I have to do there to get SYK?
Okay, I don't really know. I'm very interested, but I don't.
Okay,
I don't
thank
know.
you. I mean, I think it's interesting to understand how.
Yes, this is
CFT,
absolutely.
CFT in 4-dimension suddenly becomes SYK, because on left-hand side, it's very clear how you get ADS2.
Yes.
But suddenly right-hand side, I have to get SYK. And SYK is nothing very difficult, actually. It is, as we know very well, kind of Virasoro character. So somehow this 4-dimensional conformal field theory has there these Virasoro characters hidden inside. It's strange. I don't know. I would love to understand this.
Yes, actually, in fact, similarly, right? You can see how come there's a CFT2 whose partition function I use inside any CFTD, right? So this is this column here between this.
Well, even that, if you can explain, would be great.
Yeah, this is also quite interesting. And we don't know exactly how to start with one and land in the other. Yeah.
Thank you. And that's basically it's a very similar question, because this CFT2, which you have on the lower corner, is directly related to the left corner in ADS2 JT gravity. That can be understood. But I don't know anything about left hand side.
I think you mean this direct.
No, this is difficult. I mean diagonally. If you go CFT2, you see you have CFT2 in the left right corner in the bottom, and in the middle you have ADS2 geometry J. This is easier to understand.
I see.
This is I think I can explain that, but I cannot explain without knowing anything on left hand side how to do jumps on the right hand side.
I see.
Suppose I know nothing.
I see.
I want just to go CFT4, CFT2, SYK.
Yes.
Just directly.
Yes.
So it's all my questions. Thank you very much.
Yeah, thank you very much. No, thank you. Very, very stimulating. Thank you.
Any more questions? If not, let's thank Leopoldo for the very nice talk again.
Thank you very much.
Thanks again.
Thank you. Thank you.
Bye.